All right, so thank you very much. This is about a line of work done in Facebook AI research in Tel Aviv with Adam Polyak and Lior Wolf. And roughly in the last 4 or 5 years, we've seen remarkable breakthroughs in computer vision. It's really an astonishing time in this field, and this is mostly, not everything, but mostly thanks to deep neural networks. Now, these technologies are now widely deployed and applicable everywhere, from online photos, videos, to real-time driving assistance, healthcare imaging, and many more. Also, similar breakthrough was seen in speech recognition using deep nets as well, and we've also seen advances in specific text application, such as end-to-end machine translation and specific type of bots. Now, the common divisor to all of these advances is supervised learning. So if you can get millions of samples, labeled samples, you can probably solve any task that we as humans can do with our brains within, let's say, half a second by just training a large neural network on it. However, looking forward, all eyes are looking beyond supervised learning, also as Michal presented, mainly because it's impossible to label everything in this world. So, for example, it is impossible to collect all possible dialogue as pairs, as well as question and answers about every little piece. So if, for example, you want to teach robots to help us achieve all kinds of goals, it's impossible for you to show them every little thing. It's just not possible. Now, one approach to advance this that we and many others believe in is transfer learning, which is about finding methods that are able to learn how to transfer knowledge between domains, all kinds of domains and modalities. So if we know how to solve task A efficiently, we should be able to solve a related task B with very little effort. So in this talk, I will focus on learning to transfer between related visual domains, such as digits and faces, but in an unsupervised way. So I will start with the recent trends in visual transfer, which I think are relevant to position my talk. And starting with style transfer here. Style transfer is a method where you can edit an image, or a video in this case, based on the texture of another image, and get plausible results. As shown here, they look pretty artistic. However, the transfer itself doesn't understand what it transferred. There is no learning, and it's not semantic. The second line of work, which I think is relevant here, is domain adaptation. You can use such methods sometimes to fix a drift between the training set distribution and the test set distribution, and therefore improve overall scores, classification scores, but it's mostly done on the feature level, and it's not as generative as with style transfer, and you also don't get to see the analogies. Now, more recently, the pixel-to-pixel methods from Berkeley has shown a promising way to translate between one form to the other, but this is mostly done in a supervised way. So specifically, given two images aligned at the same location, for example, here shown on the left bottom, a map with and without satellite view, or on the bottom right, an image and its edge contour, really exactly the same location, you could generate one image given the other in a convincing way, and this is achieved using GANs, which I'll touch about a bit later. But again, it's critical to understand that this is done in a completely supervised way, given millions of such aligned pairs. However, most of the time we think, when we think about usual image transfer learning problems, we end up with tasks that have lots of images in each one of the domains, but there is no direct mapping between them. So here are some examples that generally require unsupervised cross-domain methods. So for the autonomous driving system, you wish your system to be robust to all kinds of conditions, such as driving at night. So on the left here, you see the same sample at the same time in two particular conditions, day and night. But you can also imagine snow, storm, rain, or any other weather condition, but for which you cannot get very aligned pairs, but you can definitely get lots of samples in each one of those domains easily. Another application, similarly here, is in the middle. For styling, you would want to convert bags to their matching shoes. And another cool application here on the right is in virtual reality, where you wish to transfer between the real world into a virtual one. So in this case, you have humans turning into 3D generated avatars that are being rendered seamlessly using VR equipment. And actually, more generally, transfer learning is at the forefront of AI research these days, where general tasks require more general learning algorithm. So for example, you can learn to fly drones and drive cars in a simulated environment by having a simulator, but then the problem would be how to transfer this knowledge from the simulated world into the real world. Also similarly in robotics and reinforcement learning, you want the robots to imitate humans by analogies. Now, we as humans, we believe that there is enough information in our world to make analogies without explicit supervision and actually find them automatically. So take for one example the task of drawing, or specifically cartooning, where you have a facial photo here and you want to draw its cartoon. Now, a single cartoon takes a lot of time to achieve, and even if you are Facebook, there is no way for you to get millions of aligned pairs, meaning an input and generated cartoon for them. But instead, you could definitely get lots of real faces and lots of cartoons, but again, without any mapping between them. Now, one thing you would require that, unlike stat transfer, you want the task to be meaningful. For one example, you want to preserve, in this case, identity. So in this task, we wish to transfer a sample in the source domain S to its corresponding analogy in domain T, but without being given any correspondences between S and T. Now, general cartooning has been considered in the last 15 years or so an unsolved problem with several limited attempts, but without any solution or system that existed until now. Now, these days, we have plenty of good human-level experts in several domains. So for the 1000 ImageNet protocol, you have all kinds of incarnations of AlexNet. For faces, we have the DeepFace ConvNet or its variants, and for digit, we can simply use the original LeNet. So in this work, we are interested in using such experts for the task of cross-domain image generation. Or more formally, the problem which we are solving is called the domain transfer problem. Specifically, given two related domains, we can call them S and T. We learn a generative function G that goes between them, such that for a given perceptual function F, G of X doesn't change F much when you map a sample from S to T. So the problem itself is completely unsupervised in the sense that all samples either in S or T are unlabeled, no pairs are given, like you don't know that a particular sample in S goes to a particular point in T, and F itself is both asymmetrical or unadapted in the sense that it has never seen, it didn't see any examples in the target domain T. So our wish is to build some model G here that will take a real image here on the left and generate directly its cartoon version here on the right. So our approach for this makes use of an expert in the source domain by encoding the image into a meaningful representation, f of x, shown here in the middle. And you can do that, for example, given the DeepFace network that I've just mentioned. Now, given those embeddings, we therefore wish to train a decoder G that will transform such representation to a corresponding emoji sample here on the right. The main question is, therefore, how do we train such G? So first, we want to make sure that the decoded emoji is semantically close to the source. So for this, we apply f another time, this time on a generated image, and ask that the difference between this image and the one that was the f that was applied on the input will be as small as possible. So this is our first loss, which we call the L-const loss, which ensures that the output image will be semantically close to the input, given an f. This is not enough, so we also want to make sure that the samples in T are invariant by the decoder. Therefore, we ensure that the decoded samples, which were originally in the target domain already, are invariant by the decoder and stay there. It's as if every sample T in T is actually a fixed point of this G. Now, how do we make sure that the decoded images are as sharp and look like those actually in the target domain? So for this, you make use of a generative adversarial network, or in short, a GAN. And unless you've been here in the last year, here is a short reminder about GANs. So GAN can learn two networks, D and G, simultaneously in a minimax game. So D is the discriminator here, a network which is trying to classify whether an image it sees is a natural image or actually the output of some computer algorithm. So for example, D is a convnet with a binary classification output, for example, real or fake. That would be the labels in this case. And G is a generator network with the goal of producing images that will fool discriminator D. So in fact, a generator can be a convnet too, where you simply take a vector and expand it into an image by using a convnet, but instead of downsampling, you do upsampling. So actually, to train G, you cheat by seeing network D and update its gradient in order to maximize the error of D. And this is after D actually itself tries to minimize its own error. This is why it's called adversarial, since they both play against each other in a zero-sum game. And the saddle point of the GAN loss training is the result of giving us this generator that generates images which are as undistinguishable as possible from the target domain. Okay, so overall we add this GAN component to our overall loss. But in our case, we use a three-way discriminator that needs to decide whether the image came from truly an emoji, or a generated one given an emoji, or a generated one given a natural image. So we have three options here. And this would make our third loss, which we call LGAN. So finally, this is the final domain transfer network, or in short, the DTN, presented here with all of the losses. And once training is finished, this network G is simply used in a forward manner to produce generations from pixels to pixels directly. Now, what surprised us most was the ability of the generator to pick up those f of x embeddings and without any alignment or supervision to generate their counterparts in T. So how do we evaluate the DTN? We evaluate it in two domains. We will start with digits and then go and move to faces. So in the case of digits, we take two of the most popular data sets in machine learning today, the street house numbers and MNIST, and train a DTN to transfer between them. So the expert F in this case was trained only on the street house numbers data set. So F is a standard convnet that predicts a class out of 10 options, in this case 0 to 9. And we then train our DTN to transfer what you see here on the left, samples in S domain, the street view house numbers. And on the right, you actually don't see, these are not actual MNIST digits, these are the corresponding one of the left ones. And if, for example, you wish to test street house number digits in the domain of MNIST, you simply transfer them, and then what we did is we searched for the nearest neighbor in the MNIST data set, the real one, and then we simply label the transferred image based on that. Really based on the pixel values in themselves, we didn't even train a classifier. And only by doing that, we reached performance above 84% here, which is the state of the art in this particular protocol, where all the other methods are based on domain adaptation. We also evaluated how good is the transfer in partially observable domains. So for that, we removed a particular class from the experiment, in this case, digit 3. And in several ways, we show how it generalizes to it. So in each one of these columns, we gradually remove 3 from either the source, the target, or actually both domains, and we then at DTN from scratch. And we see that the performance, although it deteriorates, it still works. However, when we remove the expert F from our architecture, we collapse to the rightmost column here, which basically includes arbitrary images, which is exactly equivalent to simply running a gun on this problem. So you overall get plausible images, but these are not semantically meaningful. So overall, we see here that there is a good generalization, and our observation is that using the expert is crucial. Back to the cartooning task, we wanted to measure how well we're doing with this task compared to humans. And for this, we asked expert annotators to use an online service called Bitmoji and build an emoji for about 100 natural facial images. This is used only for evaluation purposes. And you see here in the middle the Design Your Avatar tool, which they use to produce the images on the right. Given an input, you see an avatar based on this tool. Now, in here, we show the results of our DTN on this task. So the 4 segments here are basically telling the same. The first column is the input. The second column is the result of the annotator team trying their best to create an avatar. And the third column is the result of our DTN, which is the automated generated emoji. Now, when we ask which one is better, we can simply run a face recognition benchmark, which will tell us which one is actually more identifiable. So what we did here, basically, we took 100,000 identities and added the input image, and then we probed it 2 times, first with the automated generated emoji, and second time with the manually created one, and we record the rank. And what we see here is that the automated ones are extremely more recognizable. We get to about rank 16 out of 100,000, which is 3 orders of magnitude better than the manually created one. This overall confirms what our eye sees as well, that the automated created emoji are much more similar than the manual ones. Here are some more examples. Odd columns are input, and even columns are output. And this is actually the full set of all 80 identities of the face crop data set. So we did not cherry pick here or omit any result. All right, so as much as we like pixel to pixel and end-to-end training, we recall that our target domain was actually generated by a particular engine. So in fact, this is a quite common application called computer graphics. And the question is whether we can learn to transfer between domains where the target domain is well parameterized and not by pixels, specifically by a computer graphics engine. So here are some common examples where the target domain was indeed generated by such engine. On the left, the emoji stickers is quite popular these days. Basically, once you have a parameterization of an emoji, you can render it in all kinds of emotions and poses. Also, 3D avatars here in the middle. These are basically mapping between polygons and textures into pixels, but in a structured manner. And each one of those generations indeed initially was represented by a vector of parameters. So this brought us to revisit our domain transfer problem to collaborate with a given engine, E in this case. So in here we ask that the output will be a tied pair of the generated image, G of X, and we will also output a vector of parameters U such that the rendering will comply with the generated image. Now, once such U is recovered, we no longer use the G network that we used before, but instead we use the computer graphics engine to render a world. This is maybe presented more clearly here. So we revisited the DTN architecture in the following way. In this new architecture, we trained both G and C here. As before, we trained G to generate output which is as undistinguishable as possible from the space of emoji. This is thanks to the gun. And we also train jointly network C, which will map the generated output into a vector which the engine G, here, shown here as a black box on the right, will be able to render it faithfully. So overall, we have 2 generated images, one from the ConvNet and one from the engine after recovering its parameterization, and we ask that the difference of this during training will be as small as possible. So in this way, G and C collaborate on the loss surface together with the GAN loss and ensure that the generated image is engine compliant. So here are some tied output examples, which in each row you have the input in the leftmost column and a 3D generated avatar on the rightmost column here, which was generated by a computer graphics engine given a vector of parameters that the method that I just described recovered. So you can see that despite this avatar being a bit more minimalistic and less identifiable maybe than the emoji counterparts, the renderings comply both with the generated images, and the identity here is overall preserved. Okay, so looking ahead, domain transfer is highly related to transfer learning in general, which is a central topic in AI research these days, where we sample the knowledge acquired in one domain into the other in all sorts of modalities. And we already start to see new ways of transfer learning in other domains, such as reinforcement learning. And I believe this will continue to dominate AI research, at least in the near future. I'll finish here. Thank you.